Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Let's continue with some more physical metallurgy concepts. In this class, we will cover about ternary phase diagrams. We'll understand what is a triangular prism and then the sections in the triangular prism. Especially, we'll start with how to read the compositions and then we'll focus on certain sections called isothermal sections. So when we say ternary phase diagram, we are talking about a three component phase diagram. How to represent composition of three elements in a 2D diagram. You see, number of components itself is now 3. Then temperature is going to be one more variable, if not pressure. Then how to represent this in a 2D diagram? It's a challenge. So keep the temperature constant is one way. Vary the composition value of only two components, let's say percentage of A and percentage of B, independently in X and Y axis. A conventional perpendicular axis like this, but the composition of the third element is now dependent, and more importantly, it can be calculated like this. Percentage of C is equal to 100 minus percentage of A plus percentage of B, but this is the only way to do that. In perpendicular axis, the third element composition cannot be read directly. That is a problem. So what to do? The solution is a triangular diagram. It's an equilateral triangle. Compositions of three components in three sides are represented in this, and the advantage is this: composition of all the three elements can be read directly. Okay, so this is essentially I'm talking about an isothermal section where temperature is constant. We'll see about it in detail after a few slides. Let's first start with how to read these ternary compositions. So this is a equilateral triangle here. A, B, C, three elements are represented here. So this is basically a three elemental space, and the corners, this corner here, this corner here, and this corner here, they represent 100% of single element, that is unary composition. So this is pure A at this corner, pure B, and pure C. Then what do the edges mean? This edge here is a BC edge, meaning this is representing only binary compositions between B and C, and the amount of A along this line, is 0. Okay, you can see here, this is a AC line where amount of B is 0. Okay, so the edges are binary compositions. Any point within this triangle is going to have a combination of all the three elements in different ratios. So that's what this ternary composition space is. What is the content of A? So take this line. This line has A content 0, meaning it is only BC. So we just saw that. Now this is going to be 10% of A, and this is going to be 20% of A, and so on. So we start with a line parallel to BC, and all the lines that are parallel to BC are going to represent the A content. Okay? So this is 40%, 50%, and so on. So all these lines are telling about the A content. So here in the right side, this axis, we have represented 0 to 100. So this is A content. We could have represented on this left hand side also 0 to 100, but whichever goes from 0 to 100, and 100 should be this corner, that is going to be the amount of A axis. Right now it is in this right side. Similarly, if we want a B content, all these orange lines here, they are going to represent B content. They are all parallel to AC. If you see carefully, it's AC, that is this particular line is going to represent 0% of B, and as the lines increase, we are going to see gradually the B content increasing. So this is representing all B contents. So if you notice one more interesting fact, if you see 0A, the blue line is the longest here, and the 10% A line is shorter than that, 20% A line is even shorter than that, and so on. Similarly, this orange line also, as the length of the line decreases, the length of this line decreases, the content of B increases. Okay, so that is one observation, and this is B content. About C, all these green lines now represent C content. So AB, this extreme edge is 0% of C. So we will represent all the C values in the axis below. So 0 to 100% C increases in this manner. Okay. So that is C content. Now this triangle is called as Gibbs triangle. To know the content of A, what we did is read from the lines parallel to BC. So BC composition line you have to take and read A content with the lines that are parallel to BC, all these blue lines. And also the longer the line, the smaller the content. That is also another observation. More importantly, these lines may not be present in actual diagrams. There will be only phase stability regions, single phase, two phase, three phase, and so on. You have to bear this in mind. These lines may not be present in actual diagrams. So now let's do a small exercise of how to read the composition. Let's take this orange dot. What is the composition there? First, the blue line, which is going to be percentage of A, mainly because this line is parallel to BC. So it is showing 40% of A. We have to see where A content increases. In that axis, we have to read that. Do not read this 60. This is not A content. This 40 is A content because it goes from 0 to 100 like this. Right. So 40 is A content. And then what about B? Line parallel to AC is this. So that is going to be B content. Okay. So that is this 30. Right. So I'm using blue line for everything now. Doesn't matter. So this is going to be the C content, obviously, and that is going to be 30. Right. So this 40 A, 30 B, and 30 C is the composition. Total is going to be 100. Of course, if you have expressed the composition in terms of only two component data, 40% A, 30% B, even that is enough. So automatically C is going to be 100 minus this 70. That is also enough. But if you the advantage in this diagram is you are able to read all the three directly. You are not actually using 100 minus the other two to get the third element content. Okay, so that is the advantage here. So you can choose which two elements you want to use to represent the composition also. All right. So now this is an exercise for you, test your understanding. So pause the video, roughly reproduce this diagram in a paper and try to find out what is the composition. If you are ready with the answer, so this is going to be the answer. This line is parallel to BC. So this is telling you about the A content. This is telling you about the B content. It's going to be 28% A, this point here, and 18% B, this point here. Right. Now let's think about the triangular prism itself, meaning the temperature has one axis, three compositions just like the Gibbs triangle plus one temperature axis. So it's going to look like this. ABC, the triangle is here and the temperature is here. Of course, you cannot see it as a equilateral triangle because this is a three-dimensional object projected into a two-dimension. This is how a triangular prism will look. So three compositions and temperature are the variables. Three binary diagrams in three sides can be imagined, isn't it? Because temperature is going to be one axis, you can put this side of this triangular prism and see a binary phase diagram, right? This is just a BC binary phase diagram. So that can be represented here. In the interior, it's going to be ternary compositions. The three binaries in three sides, what if all the three are simple isomorphous systems? Okay. So this is one isomorphous system here. All the three AB, BC and AC are isomorphous systems here. How about one isomorphous and two eutectic? The AC here is an isomorphous diagram. You can see this. This AB is an eutectic system and CB is an eutectic system. You can already see that it's getting quite complex to visualize. What if all the three are eutectic? It's going to look like this. Okay, so visualization of this ternary prism is difficult. And more importantly, more binary diagrams themselves are not simple. Okay, in this case, we are saying simple, all the three are eutectic, all the three are isomorphous and things like that. But systems need not be this simple. For example, imagine the AL-Ni phase diagram that we saw in the last class. It had a few intermetallic compounds also in the middle. Even the binaries are going to be complex, therefore it is going to be difficult to visualize a ternary prism like this. So obviously, the solution for this is two-dimensional diagrams with some compromises. That is isothermal section. It's a triangular diagram like this. We can also plot something called as liquidus or solidus projections. They are also triangular in nature like this. And we can plot vertical section or isoplethal sections, pseudo-binary, quasi-binary sections. So these are all with the perpendicular axis. Let's focus on the first one, the isothermal sections. So when you want to understand constant temperature ternary sections, the edges are going to be binary, right? So this is going to be a binary isothermal section. So let us understand the edges first, starting from binary diagrams. So this is one binary diagram AB. Imagine this is a isomorphous diagram, and let's put a constant temperature section like this. So this is a constant temperature line, not the tie line. This is a constant temperature line throughout the entire composition space. And what are the phases that we see in this? So we see from this point to this point it is in alpha region, and from this point to this point it is in liquid plus alpha region. From this point to this point it is in liquid region. So single phase alpha, single phase liquid, and liquid plus alpha in the middle. This is how we see this diagram. Let us take it out and keep it aside. This is going to be our binary isothermal section. So the phases also, let's put alpha here, liquid plus alpha here, and liquid here. So this is isothermal binary section. So when we talk about isothermal ternary section, this AB is going to be in one side. Right? Let's say this isothermal ternary section is also drawn at this temperature. Then what we will see in the AB side, this entire thing that we see in the bottom will go in this AB side. Okay, let's put the phases also, alpha, liquid, and liquid plus alpha. So this is isothermal ternary sections edge, one edge, AB edge. Okay. So what if we add the C to this? Let's say this region here is liquid in the binary side. If we add some element C to these AB combinations, let's say any of this combination of AB, let's start with 70, and in that if we add C, what happens is we enter into the ternary regime like this. What if liquid is still stable? If we add C, then this entire region is going to be liquid only, even with addition of C. Right? Similarly, this alpha region, which is in the binary side, can be extended into the ternary side as C is added. And in fact, this liquid plus alpha also may remain as liquid plus alpha when C is added. Some of the amount of C that we add can go to this liquid, and some of them can go to this alpha, and this liquid plus alpha can remain. So I'm just saying a diagram like this is quite possible, that this region and with the ABC combinations is going to be liquid, and this region is going to be solid, this region is going to be liquid plus solid. Quite possible, right? You can pause and do a small test to your understanding. What is the composition and phases at this orange dot? You can roughly reproduce this diagram in a paper and work it out. This is the answer. Now let's see how these isothermal sections come from the ternary prism. This is a ternary prism. You can see ABC is represented here, and at different this is just all the three sides isomorphous kind of diagram. At different temperatures, as a triangle drawn. This is basically like taking a blade and cutting the ternary prism like that. Okay, so this is T1, T2, T3, T4 at different temperatures. You see that the isothermal sections are formed. So we are going to cut things like this. So this is the blades I'm talking about. Okay, so once you cut it, and you can visualize them separately. Okay, that's what isothermal sections are. So the variables in the axis are going to be only compositions, because temperature is going to be constant, right? So this is a small interactive animation. These kind of things are available in this source. You can try it out. It's a wonderful source. You can see here isothermal sections. An animation can be done. So you can start the animation, and if you see, there are different isothermal sections, T1, T2, T3, T4 and all are there. You can drag any of this out. Let's say we are going to drag out one of these things, T3. We are getting this solid, solid plus liquid and liquid. Three different regions are there. Liquid, solid and solid plus liquid, three different regions at T3. And if we click reset and drag the other temperature T2, here also we see this solid, solid plus liquid and liquid regions. Okay, so T1 at a very low temperature, we see it is completely solid. All the three sides it is isomorphous. So at low temperatures you will be seeing a complete single solid at all compositions. Like this, you can work out some animations also in this source. Right. Thank you. I hope the lecture is useful. See you in the next video.